Okay, everyone, it's me. I'm back. Was having some difficulty with a few things. So what we're going to be going over in this tutorial is the reinforce algorithm in TensorFlow. And we're going to be doing that for a discrete action space because our environment is going to be CartPole v0. And just a very quick recap of the reinforce algorithm. The reinforce algorithm is just maximizing the future sum of rewards. Each there's a return for each time step, and to maximize that. So what we're trying to do is learn a policy that maximizes the future expected sum of rewards, which is also known as the return. And if you were to put it into a formula, you don't put it as a return, you put it as G. So we're trying to maximize G. And we do that with respect to the model parameters, and we collect samples from the environment, and we calculate what G is, and then calculate our loss and update our network to maximize G. And anyways, so in order to implement the reinforce algorithm, we need a model that's going to be selecting our actions. We need a way to sample our actions given the model output, and we need an environment to run that model on. So we need to install Gym if you're doing it in Colab notebooks. So you need !pip install Gym, and that will install Gym. And then for the rest of the imports, you need to import NumPy as NP. I don't think we'll need statistics right now. Import TensorFlow as TF. Import TensorFlow probability as TFP. From tensorflow.keras, import layers. And we also need to import Gym for our environment. And that's it for imports. And to create our environment from Gym, so Gym is provided by OpenAI, and they have some environments that are available. This is the one we're going to be running on today, but it's called CartPole v1, but we're going to be using CartPole v0 in Colab, because if we put CartPole v1, it'll just give us an error. And it'll tell us to use v0 instead, so we're going to use v0. So we make our environment by calling gym.make and pass it the name as a string of which environment it is, which is CartPole v0. So we now need an actor that is going to be outputting logits to select actions for. So we need to know how many actions there are potentially for our environment. And for Gym, we know for CartPole v0, each environment is going to have a separate number of actions. And this one is it only allows you to do 2 actions, left or right. So the number of actions that we have is 2 actions. Okay, so we can take 2 actions in this environment. So what we do is we create a model, and we're going to call our model actor, and it's going to inherit from tensorflow.keras.model, and we just call the constructor on this model class, and in the initialize method we call it with the normal parameter self. It needs to know how many actions the model is going to take, like how many possible actions it can take, and we're going to have a hidden layer, and it needs to know how many units are in that hidden layer. So need to call actor actually inside that super method. So we're going to call super with actor as an argument dot underscore init, and we're just going to define a couple layers. We're going to have our first hidden layer is, we're going to call it self.shared. It's going to be a dense layer with number of hidden units, and the activation function for this hidden layer is going to be ReLU, and this is going to be our output for our actor class. So we're going to call our output layer self.actor, and the number of so we're going to create a dense layer, which is layers.dense, and the number of outputs that it has is the number of actions that we can possibly take in the environment, which is just the number of actions. So we need a call, constructor call method, and so we define call, pass itself as an argument, and the input observation that we're going to be getting to run the model on. So we call our first hidden layer on our input observation, and we call that x, and we call our output layer on that hidden layer, so self.actorX, and we're going to return that, and that's going to be a forward pass-through model. So, so to actually create a specific instance of our model, we're going to call actor with the number of actions we have, which is 2 actions, a number of hidden units, which is 128. You can change the number of hidden units you have in your network and number of hidden layers also you have in your network, depending on the problem you're trying to solve or whatever. So we talked about return earlier, and return is just the expected discounted sum of all future rewards. So and a lot of tutorials, they do this thing where they flip the for example, if you have an agent that's in an environment and it goes through 100 time steps, you're going to have a trajectory of 100 time steps of actions and 100 time steps of rewards, or 100 time steps of the probability of those actions, and you're going to have to be able to calculate what the future sum of discounted rewards is. So the way that I had done it was, so you discount future time steps, so so you don't end up with infinite reward, so reward converges. And the way that I did it is, so you need to know how much you're discounting your future sum of rewards, and that value is known as gamma. So you take a reward trajectory from running on the environment, and what you do is you sum all the future reward, but each future time step gets multiplied by gamma to the n. So for example, if we're at the first time step, if we have gamma to the 0, it's actually going to equal 1. So we get the exact reward we get from that time step. But all future time steps, if gamma was 0.9, the 0.9 to the first is going to be 0.9, and 0.9 to the second is going to be 0.81, and so on. So this is just an easy way to do that. Well, it was easy for me. So we find out the length of our, of our reward trajectory, how many time steps we have, and we're pretty much just writing how much discounting we're going to be getting for the entire length of the trajectory, and we put that into a variable called easy discount. And we haven't calculated any of our returns yet, so we're going to have our returns stored in a list. So we're going to initialize an empty list or define an empty list. So we get our reward trajectory as an argument and gamma as an argument, and we're actually done with gamma at this point. So what we do is we take our reward trajectory and we convert that into an array, because we actually get it passed as an argument from our episode stepper. So for every step in our reward trajectory, we need to compute what the future sum of discounted rewards is. So we pretty much create a list which is up a single time step in our reward trajectory until the end, okay? And that's all the rewards until the end of the episode. And we already know that, we need to find out what the length of, the number of time steps there are left in there, and we're going to index, easy discount by that. So we're going to end up with a list of all the rewards until the end of the episode, and a list of our discounting factor, which is easy discount, and we're going to multiply those together, and that's going to be what the rewards are for the rest of our time steps for that episode, and we're just going to take the sum of that, and that's going to give us G. And we're going to take that value G, which is just for a single time step, and append that to our trajectory for all of the returns for all the time steps, which is G's, and we're going to do that for all time steps. So this is just one way that you can go ahead and calculate future sum of rewards. Some people might not like this method, some people might. It works, and it's actually, to me, this feels very clean, like using a comprehension like that, and then just applying it to like a sliced list of the reward trajectories, and then multiplying it by that list to apply the discount factor, and then taking the sum of that. So that's all we're doing right here. Yeah. I actually probably should have gone over this after talking about how we step the episode, so I do apologize, but we're going to talk about how we step the episode. So we've already defined our environment in our model. Okay, I'm going to just move that down we're going to ignore it next time. So we need to step our episode. So reinforce is like a episodic learning algorithm. So we need to go ahead and collect an entire reward trajectory, entire action trajectory for all time steps in order to compute the algorithm. So what we do is we reset our environment to get it into its starting state, and we call that observation. And we just define our two lists that are going to be kind of like our trajectories for the time being. So we define one list as our action probabilities list, and we define one as our rewards list, because the actual algorithm for reinforce it's the negative log probability of taking some action in some state multiplied by our return for that time step or that state. And that return is our G, and we get that from our rewards. So we're going to get this reward, and we're then going to calculate G afterward, and then we're going to use that G to compute our loss. So since we barely started the episode, we say done is equal to false, because we're going to need to determine, when it's the end of the episode, we're going to break and compute. So, if done, break. Otherwise, we're going to go through this loop through the whole environment. We're going to say our observation is equal to tf.expanddims, which is our observation, which was given to us by our environment, and 0 for our index for expanddims. And the reason that we do tf.expanddims on our observation before feeding it to our model is the reason for doing that is because our model is going to expect a batch of inputs, and our observation is just a single observation. So we need to add a batch dimension, and that's what tf.expanddims does. So we take that observation and we pass it to our model, and our model is going to return our action logits to us. So now our model has constructed, made some predictions in the form of action logits, and the output for this model is going to have, two values, because we have two actions. The number of actions we have, the number of nodes in our units in our last layer is 2. So we're going to call tensorflow probability.distributions.categorical on our action logits, which is just 2 values, and we're going to get a discrete distribution back. So we're going to go ahead and we're going to sample a single action from that discrete distribution, and we're going to call that our selected action index. And this is returning something as a tensor, because this is TensorFlow. So what we need to actually do is call selected action index.numpy to turn our selected action index from a tensor to a numpy array. And this is still a batch of a batch of actions. So we need to just make sure that we're indexing the 0th action because our environment.step argument, because we need to call the environment, hey, we now have an action, to get to the next time step, an action to take. So we need to pass our action to environment through the environment.step method. But since we're using Gym, it's not going to take a tensor. It's going to take a numpy array, and we need to make sure we pass it the 0th element of that numpy array that we sampled that action from. And in return, our environment.step function is going to return a few values. It's going to return a new observation, the reward that we received from taking that action in the previous state, whether we're now currently done to end the episode, and some information that we're just going to throw away. We're going to completely disregard that right now, but it returns 4 values to us. So we need to calculate we need the probability of taking an action in a state, because for the loss we're going to need the log of that probability. So we're going to call discrete distribution.probability of taking a selected action from this distribution. So this is going to be the action prob of taking this action given this distribution, and we're going to go ahead and add that to our action probability list. And the reward that we received from taking this action, given the state, we're going to receive a certain reward, and that reward we're also going to add it to our reward trajectory. And we're going to do this until it's done. We're going to call environment.close, and we're going to return our action probabilities list and the rewards. Okay. So let's go ahead and talk about our loss function. So, whoops, I'm going to go over this in the correct order. So we're going to need to calculate our G's. So we have a function called complete loss, and it takes our action probabilities and our rewards. And now that we have our rewards, we can calculate our G's, which is our return, which is the future expected sum of rewards. So we call calc G, which is this function right here that we've been over, with our reward trajectory and a discount factor, which is gamma. And I just defined it as 0.99. 0.99 is very common for example problems, because it still has a fairly long time horizon, but it's still discounting the rewards. And then we call the actor loss function on our action probabilities and our G's. So what happens inside of this actor loss function, and obviously we're going to return the output from this function. So what happens inside of here, it takes our action probabilities and our G's, and this is the algorithm for reinforce, which is the negative log probability of selecting an action given a state times our expected discounted reward. Whoops. Discounted reward, which is our G's. Okay, so we now have our action probabilities, and we need the log probability. So we're going to call tf.math.log on our action probabilities, and it's going to return us a list of our action log probabilities, and we need to multiply those action log probabilities times our G, given this this formula, and we need the negative of that. And the reason that we need the negative is because our optimizer is going to so reinforce is technically gradient ascent, because we're trying to maximize our future sum of rewards, so we can expect more rewards in future time steps. And our optimizer by default, it's minimizing a loss. So in order to maximize our future expected sum of rewards, what we actually have to do is give it the negative. That way, so the negative expected future sum of rewards, if we minimize that, that's actually maximizing the true negative sum of rewards. Anyways, and we're going to return that, and that's going to be our actual loss that gets computed. And we need an optimizer, and we're going to have a step size of 0.001. You could have 0.0005. Just a very small learning rate will do well. And this is just for logging. We have an average reward here. So let's go ahead and train. So don't need 20,000, don't even need 2,000. So we're going to say for episode in range 2,000. So this can train for up to 2,000 episodes, unless we get too early stopping, which we'll go over. So just the way that we train any model, we're going to say within the scope of tf.gradient tape as tape, we're going to go ahead and step our episode given an environment and a model. And our step episode function is going to let us know what the action probabilities are, for each time step, and the rewards for that time step, for a list of rewards for every time step. And then we have our loss function, which is going to go ahead and compute our loss given these action probabilities and episode returns, and we already went over that with what happens in there. And then, yeah, we go ahead and we find our gradients. So we call tape.gradient and we pass it our loss and our model.trainable variables. And we'll go ahead and, find the gradients for us. And we're just going to say optimizer.apply gradients. And we're going to zip our gradients and our model.trainable variables. And this is just some logging that we're going to do right now, which is we're going to log what the average, what the reward was for any one episode, and then every 20 episodes. So if episode mod 20 is equal to 0, we're going to print what episode we're on and the mean of the rewards for the last 25 episodes. And also if on average the mean of the rewards for the last 20 episodes were greater than 175, we're going to break. So I'm going to go ahead and hit play just so you guys can see this train for a minute. And I'm just going to end it very quickly. We might not get to 200 reward. So just like how we're supposed to know how many actions there are to take, it's also good to know like what's the expected, reward. So, whoops, that's not good. It was running before I did that, so hold on. Do apologize. I guess I'll deal with that later. Just 1 minute. Hold on. Gotta reset everything because I wanted to train. Don't want to re-record this video. So it's good to know how many, what the expected reward is to say that like you've successfully learned the correct actions in an environment or whatever. So for this CartPole, if you have a reward on average of 200, that means that like you've learned everything as well as you can. But if on average you're over 175, it means obviously that's much better than getting an average reward of 13. Like obviously 175 is much higher. So we're trying to, remember, we're trying to maximize the reward. So on average, this value should be going up. And this is just an early stopping condition if we're getting closer and closer. Like it doesn't have to actually hit perfect 200 for the last 20. It could just, on average, if it's getting like 175 or like this is an arbitrary value, but I just wanted to show that like we're doing early stopping, and this would be a point where also before that break statement you would put model.save, because now your model has trained to a point where it has learned, so you'd want to save that model to run it on the environment in the future. So you can see we're slowly increasing, and reinforce is a Monte Carlo method, so it's learning directly from experience. So it does have to gather like a lot of experience, and it is on policy because it's updating with respect to current model variables or parameters or whatever. But yeah, a lot of this code I view it, I just read it once or twice before I do the tutorial because it's like close to a year old or whatever. So I do apologize if I'm not the most well spoken with these tutorials, but it's to get you guys going, and you can see that we're still continuing to maximize our reward after 380 episodes. We're like close to 80 as compared to the beginning. We were just randomly getting around 20 reward of 20. But yeah, I'm just gonna probably call it. I'm probably not gonna wait for it. I feel like I had something to say, but probably just more apologies that like these videos are not the best, but you guys can obviously copy the code and use it in your own stuff. And like I haven't seen anyone calculate G like this. Maybe it's not the most efficient method because everyone does like the reverse trajectories for some reason, which I don't see how that's more intuitive or better or preferred method, but it's just easier. And anyways, yeah, so you can see it is maximizing future expected sum of rewards. We're close to 141. And oh, look, it stopped training. So it didn't log it because this is not like out here. But we can now determine that, you know, the last 20 episodes we got reward greater than 175. I should have had it print done right there, but I didn't. Anyways, that was it for this one. Hope this clarified a little bit about reinforce and, you know, using TensorFlow for categorical or discrete action space. Like, comment, subscribe. Let me know what I could do better. I'm trying to be better. And I think I will start linking the GitHub and in the description so you guys can have access to the code. I still need to upload the code to GitHub. I just have everything on Colab notebooks right now. So anyways, you all have a wonderful day and take care, and, you know, continue studying. It's pretty fun stuff. Anyways, peace out.